Okay, so I teased in the last video that sometimes our eigenvalues are obviously not real value. Sometimes they're complex. And so we're going to address that here. We're going to see what to do in that situation. I'm going to show you a long-handed way of doing it. At the end, if I think it makes sense, I might give you guys a little kind of shortcut. But I think it's important to be able to do it the longer hand way. And the shortcut is, I don't know, it can be more confusing, to be fair. So we'll get there. We'll get there. We'll see what we're feeling. But the important thing here basically is Euler's formula. So Euler, a famous mathematician, a lot of people say his name Euler. I don't have any problem with that, but it is pronounced Euler. And so, you know, sometimes people like to kind of turn their nose at the people about that one, but honestly, you know, I think everyone's legit, you know what I mean? Like, there's no wrong answers, it's math. Anyway, he came up with this wild formula, which is basically just that e to the I pi is equal to cosine, or e to the I t is equal to cosine t plus I sine t, which seems absurd, right? You take some exponential function, you raise it to an imaginary number, times t is assumed to be some complex number, and you get a sum of cosine and sine functions. Like, that's absurd, right? This comes from, if you look it up, there's some great math behind this, really interesting stuff. This is, well, it's one of the most important formulas in math. In fact, if we plug in pi for t, look what we get. We get e to the I pi equals cosine of pi is -1. And sine of pi is 0, so the imaginary part goes away. So we get this. So typically, if you've ever seen this written out before, this is one, some people call this Euler's identity or Euler's formula or something like that. But what's cool about it is it has all 5 of the most important numbers in mathematics all in one relationship. So we've got 0, we've got 1. We've got e, we've got I, and we've got pi. So the only things we're using here are these, like, you know, giants in the worlds of mathematics. Like, these are the numbers people care about. We've got additive identity, multiplicative identity. We've got e, the natural exponential. You know, we've got the imaginary. We've got the relationship, which is, so these are used all the time. And if you think about this relationship, it's kind of wild. You raise e to the I pi, and you get -1. What? It doesn't make any sense, but it does make sense. If you really are interested in this, you should go into complex analysis, which is a field of mathematics where they study this all the time. You get really used to it. Yeah, so I am just going to jump right into it, but I just wanted to give that little precursor because we're going to use this formula a couple times. So what we so let's just get into it. So we remember from our last example that we're given some problem like this, some system of differential equations like this, and then we've got this matrix A. And remember, last time we boiled the problem down to basically just finding eigenvalues and eigenvectors, and that will kind of solve the problem for us. If for the astute among you, you may notice I'm pulling this directly off of the written example that I've included on this sheet as well. So if you want to kind of work through it or try it out first, go ahead and do that. But yeah, so let's just get right into it. So I'm going to kind of skip to the punchline here. Let's find these eigenvalues. So if we do this, we're going to get a characteristic equation that's like, you know, 3 minus lambda times 1 minus lambda equals, or I'm sorry, so plus, I guess, 5 times 13 is 65. 65, or that's 16. That's a different number, turns out. 65. And we want to know when this equals 0. Remember, this is our determinant a minus lambda I equals 0. So multiplying all this out, we get, I believe, I'm going to cheat a little bit here and copy off of the example just for the sake of time. I don't want to waste you guys' time. You got cool stuff to be doing that doesn't involve math. So cool, so we get this quadratic polynomial. Turns out that the solutions, so the eigenvalues, are going to take the form. So 1, 2 equals 2 plus or minus 8i. Okay? So clearly this is a complex number. Remember, this is sort of coming from, we get some square root of a negative somewhere, so now we get this I sitting there. You could probably hit this with the quadratic formula. There might be a way to factor it if you're super good at factoring complex numbers. I'm not super good at factoring complex numbers, so I typically just do quadratic. So cool. So what have we got here? So we know that we have two eigenvalues sitting here. We have a plus and a minus, but there's something a little funny about these complex eigenvalues. Namely, I'll be first to admit, I'm not 100% certain exactly what it is. I suspect that these eigenvalues create basically so they'll create two solutions, right? We could go through the whole process and use our kind of our e to the whatever guess, e to the lambda t guess, and do it that way. But I think what happens is the x1 and the x2 that you get are not linearly independent, which is crucial because remember our general solution is a linear combination of two linearly independent vector functions. So if our vector functions aren't linearly independent, then we can't get a general solution for that. So I'll show you how we get around that issue. And it actually is some pretty cool math. So here's what we're going to do. We're going to just consider the positive of these two. What you'll realize is that what turns out being most important are the real and complex coefficients. We'll see how that plays in a moment here, but for now, let's just think about it as we're going to say that there's lambda, and it's just 2 plus 8i. We're going to forget about the minus for now. So cool, so if that's our lambda, let's find our eigenvector. So if we do that, then we get, so let's just do it. So we get 3 minus 2 minus 8i, then we get negative 13, and then this is the first column. I didn't realize it's confusing. So there's 5 below it, and then 1 minus 2 minus 8i. Okay. So this is what we're looking at. Whoa. We want to know what vector, when we multiply it times that, is going to equal 0. Okay. So the 0 vector. Anytime I write 0 in this equation, I mean the 0 vector. So cool. So let's just go ahead and solve this. So we get, it looks like we get 1 minus 8i minus 13, and we get 5. 1 minus 2 is negative 1. So negative 1 minus 8i. Okay. So remember, the whole point of doing these eigenvalues is that we get a dependent matrix. So believe it or not, there is some constant where if we multiplied it times this column, it would be kind of the opposite of this column, right? There's something we could multiply this times to get 13 that would also make 5 1 plus 8i. But another way of just thinking about that is if we just look at this equation, so we remember, we're interested in multiplying times some vector, and we want to know when that equals a 0 vector. So if we just do the multiplication for the first row, remember that this was like a z1, z2 kind of vibe. So all I'm doing here is the vector multiplication. Oh, that's not a vector. The vector multiplication. We want to know when this equals 0. So can we find a z1? If we can find any z1 and z2 that makes this equal to 0, we do need to check, but I'm going to skip that part because I'm pretty sure it's going to work. Yeah. So I mean, like, what can we do here? Let's think about this a little bit. Basically, we want to find some z1 where when we multiply it times this, we get 13. So what happens if we just do? Would that work? Oh, that would give us 9. So the thing is, if this has to be a well, here, tell you what, I'll pause the recording and I'll come back with the answer because I'm spiraling here with these complex numbers. Okay, I cheated a little bit and checked the written solution, but this totally makes sense. Oh, I also changed. We're looking at this part now. So this was a little silly of me. If you solve this, you get 5z1 equals 1 plus 8i z2. Okay. By the way, I'm just looking at this row. I pulled the -1 out. So when we subtract it out, so you know that z1 is equal to 1 plus 8i z2 over 5. So what you do is you go, okay, well, any solution of this will work, right? So if we just make z2 equal to 5 and z1 equal to 1 plus 8i, this will work, right? Because we take z2 and multiply it, it cancels the 5, and then we're just left with that. So that's exactly what we do. So we say that our eigenvector, actually I'm just going to call it z. Our eigenvector is equal to this vector. Okay. Now, let's put this together. So we have our eigenvalue is up here, remember. Our eigenvector, I'm going to do this kind of over here. So our solution, or our kind of a more specific solution, I suppose, is this. So we get 1 plus 8i, 5. This is our vector. And then we get e to the 2 plus 8i times t. Okay. So great. So what we like here, I guess I probably should have mentioned this up front, but what we like here is we would like a general solution that doesn't involve complex numbers. That's possible. And what's kind of wild is that it is possible. And I'll show you how to do it. But the reason we don't really want complex numbers is because these systems are typically meant to describe things in sort of the real plane. And if we've got complex numbers kicking around, we're sort of adding another numerical dimension that we're not interested in contending with. So ideally, we try and remove them. And I will show you how to do that. So what we do is you can divide this up. We look at this power. We can divide it up. So we end up getting, we get, let's see, 1 plus 8i, 5. And then we get e to the 2t and e to the 8it. Now, what does this look like to you? I'm kind of hinting at it here. We can use Euler's formula on this. We've got something with a t and an I in it. Now it's important to remember. So a to the it. This is for the case where the coefficient on I is 1. But so we've got an 8 sitting there, but that's more than okay. What that means is we can write it like this. So we take our eigenvector. That's probably a little small. 1 plus 8i e to the 2t, and then we're gonna use Euler's formula here. So remember we can express this as cosine of 8t. That's where the 8 goes. It sits right in front of the t there. Plus I sine of 8t. Now I can hear you all yelling right now. Jake, there's still a lot of I's in that. You're right. You're absolutely right. But we're going to do some pretty cool math, and we're going to get rid of it. Okay. So remember, this is one of our solutions. Okay. Now, what I'm going to do here might seem a little weird, but we're going to do it anyway. We've got e to the 2t, and then I'm gonna actually multiply. Remember, all these things are being multiplied together because they're not matrices. We can commute them. So I'm going to multiply this vector over onto this guy, right? So because basically we just have like a sort of a scalar function and a vector, we just kind of multiply it in. So what we're going to get is we're going to get e to the 2t times this big old vector, which is 1 plus 8i times cosine 8t plus I sine, sorry, this should be in parentheses, I sine 8t. And then we're going to get 5 times that. So I'll just do the distribution there because it's a little easier. Okay. Do you believe me that these are equivalent? I hope so, because we're going to move forward. So if we do this distribution, we're going to get, basically we're going to get, oh, we got to FOIL it out. So we get, don't forget your e to the 2t. That's a big thing that I always do, is forget to write that out in front. So we're going to get cosine of 8t plus 8I cosine of 8t. I'm kind of foiling this weird, but I hope you believe me. Plus I sine of 8t. Minus, because the i's multiply together to get -1, minus 8 sine of 8t. Okay, remember on the bottom we have 5 cosine of 8t plus 5 sine of 8t. Now, wow, we have really created a monster of a vector. Remember, this is a vector with 2 entries. This is like a 2-dimensional vector. But it's just our top one is this huge sum of, well, both of them are these big sums of sine and cosine functions. So what we're going to do, this is where the magic comes in. We're going to collect all of our terms with an I in it and everything without an I in it. And we're going to look what happens. So if we do that, I'm kind of going to skip ahead a little bit here, so I'm sorry that I keep doing that, but I hope this makes a little bit of sense. Let's look at the numerator, or I call it the numerator. Let's look at the first component of this vector. So what terms don't have an I in it? We've got cosine, looks like we've got cosine of 8t. And then, okay, that's got an I in it. This one's got an I in it. This one doesn't, so minus 8 sine of 8t. And then let's look at the second component. Okay, no I and an I. So we're gonna just keep this one. Actually, I'm gonna put this in parentheses. Okay. Dope. So now we're gonna add, and this is what's cool. We factor the I out, because remember, everything left is gonna have an I in it. That's why we're separating it out. So we're gonna factor the I out. We're gonna say it's I times. Now let's look at the terms that have an I in it. So 8. Looks like in the first component we have 8 cosine 8t plus sine of 8t. And then in the denominator, I keep saying that, in the second component, we get 5 sine of 8t. There we go. Remember, we've got e to the 2t multiplied times this whole thing. So now, again, I can hear you all yelling at me right now. How could this possibly be simpler? What does this achieve? We still have an I in it. There's all these questions. Well, here's the kicker. Here's the cool math. You can check this, and I would encourage you to. I'm not going to do it here because it would take a long time. But if we think about, remember, this is a vector function, right? This is a vector it depends on t. So it's a function of t, and it's vectors. It's a vector function. If we call this vector function u of t, so this is the real part. You can also think of this as just a complex vector function, right? So there's a real part, which is our u of t, and then what I was just going to say is we've got a v of t sitting here, which is our complex part. Now notice v of t is not including the I. I'm only talking about the part that's in the brackets. So the actual vector, the vector coefficient, which if you look is entirely real value. It turns out that, and again, like I said, you can check this by plugging it in. Both of these, when you multiply them times e to the 2t, are solutions to the differential equation. So they solve the linear system that we were given. They solve this. And not only that, they're linearly independent. So what does that mean? That means we have 2 linearly independent specific solutions to our system, which means we can make a linear combination of them, and that's our general solution. And we're done. So we didn't even need to worry about the other eigenvalue. So what that means is, so let's bring this all together. So we've got e to the 2t times. Remember, we want a linear combination of these two things. So actually, also, I'm just gonna write it like this. So we've got c1 e to the 2t times cosine 8t minus 8 sine 8t, 5 cosine 8t, plus c2 times, remember we need our e to the 2t here still because this was getting distributed over everything, times our v of t, which happens to be this vector function here. So 8 cosine 8t plus sine of 8t. There you go. There's a general there. This is a general solution. This is x of t. Okay. Now there is what I was going to say about a shortcut is that there is a way of writing this where you basically you get something related to the eigenvector times a linear combination of sine and cosine functions instead of having these big vector functions here. What I would say is this is a perfectly acceptable form on an exam or a homework or anything. Maybe I'll leave it as an exercise. What you can do if you decompose this, right, into so you basically you would write this as cosine, because you see that we've got these cosines of 8t's, so we can factor those out and write it as maybe I'll just do this first one for you and I'll leave the second one as an exercise. So you could write this as this vector times cosine of 8t minus or actually let's just do plus and then negative 8 0 sine t. So I hope you see if you do this multiplication and add it together, you get the same thing here. You could do the same thing here, and then you could combine all the sines and cosines together, and you could get something of the form of like a constant times e to the 2t times this. And then if you look close, if you do all this combination and you look at these vectors and how they correspond to the real and imaginary parts of our eigenvalues, I think you'll see something cool happen. So I'm going to leave that as an exercise, but yeah, if the rest of this method made sense, then again, it's once you get pretty good at it, it's relatively straightforward. I think this problem is probably more convoluted than might be on an exam, but yeah, so there you go. So complex eigenvalues, we did it, and it was all thanks to our good friend Euler. So yeah, thanks for watching.